Greetings, salutations, all those things. Welcome to topic 6. Topic 6 is about exponential and logarithmic equations. We've looked at exponential functions, we've looked at logarithmic functions. Now we're going to see these things in equations, things that we can solve. Our initial exponential equations that we look at are ones that we're going to be able to solve without having to employ logarithms at all. But eventually we'll get to a point where we're going to have to, and it's going to be all sorts of interesting. The premise behind solving an exponential equation that we don't have to use logs in is that if we can get two powers that have the same base that are also equal, then we can say that their exponents are equal. So looking at this case, if 2 to the x is equal to 2 to the 7, the only way that that could be true is if x is actually 7, if these exponents are equal. And that's because, of course, an exponential function is 1 to 1. So every input value has only one output value. Every x only has one corresponding y. And there's no x that has two possible y's. There's no y that has two possible x's. So that's why we have that reality set in. In a case like this, then, we don't have the same base, but fortunately, 4 is a power of 2, and we can rewrite this so that that common base does exist. So if I were to tackle this, I'd keep this as 2 to the x, and I'd change this 4 into a 2 squared. So 4 to the power of x plus 1 is what was on the right side. Using exponent laws, I can simplify this a bit, and I can say that 2 to the x is equal to 2 to the power of 2x plus 2. Since power of a power means we're multiplying the exponents, that's all that I've done there. And at this point, we just straight up have power equals power. And that's, of course, with the same base. Because if we have that, then we can proceed. And we can say that as a result of this, therefore, x is equal to 2x plus 2. And then we're just solving this equation for x. Negative 2 equals x. Boom, done. So that's that. I dare you to try the next few that are on this page. So pause the video, give it a try, see what happens. I'm of course going to proceed, assuming that you've paused. Alright, 3 to the x minus 3, 27 to the 1 minus x. They can both be expressed as powers of 3. So the left side is already like that. Alright, right side is not. So I'll rewrite 27 as 3 cubed. Woo! Simplifying. Oopsie daisies. That. And at this point, we've got 3 to the something equals 3 to the something. Right? And we can have our, therefore, the exponents must be equal. So just to reiterate there, it's very key that we're doing this step only once we have a single power equals a single power with the same base. So if you don't have that, we cannot proceed. It's an error that I've seen a few times, so be advised that it exists. Anyhow, solving this, adding 3x both sides, adding 3 to both sides is that. And of course, we'll simplify. That's done. Whoop. 1 over 8 cannot be expressed as a power of 4, but both of these can be expressed as powers of 2. And that 4 is 2 squared. And 1/8 is 2 to the negative 3. So simplifying that a little bit on each side. that to the power of negative times negative is positive, and 3 over 6 is 1/2. All right, power equals power. I can say then that the exponents are equal. Solve this however you want. I have a tendency, sometimes I like to get rid of the fractions right away. So that's all I'm doing here. Just multiply both sides by 2. But if you have a different method, go for it. And that one is done. And the final example on this page, oh, there it is. Can't express 27 as a power of 9, but we could say that they have a common base of 3. So 3 squared to the power of 2x is equal to 3 cubed to the power of x over 3 minus 1. Opening up those brackets, we get that. And 3 times x over 3 is just x. 3 times negative 1 is negative 3. So there's that. And now that we have that, we can say that the exponents must also be equal. And we'll just solve for x. So that's the core principle of solving exponential equations. As we play around with this, we're also going to just take a look at a couple of types of real-life examples. Now, we're not going to look at every single possible type of that, but we'll get a feel for it here. We can only solve exponential equations right now if we can get them into the same base, and we're going to have cases where we can't. And right now, our only option is going to have to use some sort of guessing and checking. We can use our calculators as well if the situation allows us to do so. So this particular question right here is one you would be allowed to use your calculator for. When you invest P dollars in an account that pays R interest compounded n times per year, the value of the investment after T years can be found using this equation over here. So P is often used for principal. That's your principal amount, your initial amount. R usually stands for rate. N is your number of times compounded per year. And T is for time. A, I believe, is usually used for like the accrued amount or the accumulated amount, but that's the essentially final amount of the investment or loan or whatever it is you're playing with. So, one wishes to deposit $2,000 into an investment account with an institution that offers an interest rate of 4.2% compounded monthly. We're going to write an equation that models the value of this investment over time, basically putting everything we know into here. And that this $2,000 is our principal amount. Where's our rate? Our rate is here. So there's R. Compounded monthly means that N is 12. We're compounding 12 times per year. So plugging all that in, we're going to say that your accrued amount is equal to 2,000 times 1 plus 0.042 over 12 to the power of 12t. So that's the equation that will get you what the investment value is after t years. What will the value of the investment be after 3 years? Well, then we're just kind of plugging in to the equation. So we've got that A is equal to 2,000 times 1 plus 0.042 over 12 to the power of 12t, but t in this case is 3 years. At this point, it's just calculator work. Do be very careful how you're plugging things in, just with regards to brackets. So when you punch this in, you can say 2,000, say times put your brackets in here. 0, 4, 2 divided by 12. That's fine. But make sure that when you put in your power, you actually put brackets around the 12 times 3. Or just type in straight up 36 if you want to do that computation. But if this isn't in brackets, you're going to have a bad time. So make sure that's done. The value you should get out of here is something like this. Rounding to 2 decimal places in this case because we're dealing with dollars and cents, and your value of an account is not going to be in fractions of a cent. Doo-doo-doo. So contextual problem requires a contextual answer. We can see the value of the account is $2,268.07 after 3 years. Now this last part of the question, after how many years will the account's value have doubled, that is something where we will have an exponential equation. And again, right now, we don't necessarily have the tools to solve that algebraically. So right now, until we have those tools later on this topic, we're going to have to use essentially a guess and check method. Now, for sure, the amount of years has to be more than 3. Right? Because after 3 years, we have not doubled. We've gone up by $200. If we're doubling, then this 2,000 must have to turn into like 4,000. So if it hasn't reached 4,000, we haven't doubled. So we're going to try things, and we're going to use a little bit of number sense to decide what to do. Feel free to try some values at this point. So plug in different values for t and see how many guesses it takes you to get to the answer. See how many years, see how many whole years we can say it takes for this account value to double. Hopefully you paused, hopefully you've tried a few values. I would say, for me looking at this, I'd probably start with trying 10. After I establish it must be more than 3. So I try 10, in which case I'm using this formula to the power of 12t. T in this case would be 10. And when I evaluate that, I get this value, which is not double. So this is not enough. Dang. Maybe I'll try something else. So okay, I'll try something higher. Maybe I'll try 20, and I'll use that same formula again. But now for time, I'm plugging in 20 years. And when I put that into my calculator, I get a value of 46.2594. And this one might be a little too much. So maybe it's something in between there. I don't want to go too far down. Although like 15, 16, 17, 18, I think those all make sense to try. I'm going to try 16. So again, same formula. With 16 as the number of years. And for that, I'm getting, this, which is so close. So I think it makes most sense for me to next try 17. And hopefully that's enough. And if it's not, then we try 18, I guess. But 17 is my number of years. And when I plug that in, I get this value. So what we're noting there is that after 16 years, the value has not doubled yet. It's close, but it's not quite there, so we can't say that, yeah, 16 is sufficient. After how many years can we say that it has doubled? We can say after the count value has doubled after 17 years, and no sooner than that. When it comes to this kind of guess and check, you'll notice I kind of tried to hone in on it. So I went a little higher, went a little lower. It's kind of a game in that sense. When I initially did this, I also tried 18. So after I tried 20 and I saw 20 gave me 46.25, I figured I'll try 18, which still got me a bit too high. So I actually had that right in between these steps. Like right over here is where I tried 18. And that was too high, so I went down to 16, I tried 17. And that's how I got to it. So hopefully it didn't take you 80 guesses. But this is something that you're going to want to try and develop. There is some practice work for you to work on this. Some of these are straight up exponential equations. Some of these are a bit more word problem-y things where you're going to have to use a little bit of number sense to get after the correct answer. So give that a try. As always, please let me know if you have questions or comments or concerns. That is still on you to let me know. So voice your concerns, because if you don't, then I don't know that you are experiencing any issues. If there are issues with this lesson or issues with any of the practice work, make sure that is something that you are making sure I'm aware of. That is it. That's all for today. I will see you in the future. So long, farewell, the end.